Connectionist Temporal Classification, or CTC, is a strategy often employed when training neural networks for automatic speech recognition. In this video, I will present a derivation of CTC, which is similar to that presented by Alex Grave in his 2006 paper. Consider, for example, an audio recording which contains the word connection. An automatic speech recognition system aims to, given the audio sequence, produce the correct transcript as output. This can be accomplished by learning a phoneme to grapheme mapping, or more simply, a mapping of sounds to letters in the alphabet. However, this is a challenging task, firstly because in general we do not have accurate timestamps mapping when these sounds occur to the respective characters. Sounds may also map to multiple characters, and multiple sounds may map to a single character. This complexity is compounded by variability across speakers in multiple factors such as pitch and speech rate. Within the automatic speech recognition framework, we generally encode representations of speech at some fixed interval. These representations are then fed to a neural network, which produces a series of vectors, known as hidden state vectors, at its output. Modern transformer-based networks, such as WAV2VEC, receive as input the raw audio samples. Classically, however, the audio samples were encoded to some spectral representation, often using the Fourier transform, before being presented as input to the network. Each of these hidden state vectors are fed through a fully connected layer whose output dimensionality is the size of the target vocabulary, which is either the number of unique characters or the number of unique phonemes. By passing these vectors through a softmax layer, we can obtain probabilities for each character per time step. What we aim to achieve then is a strategy to empirically determine when these output probabilities are a good representation of the target transcription. Consider, for example, the 8 output vectors shown here, whose scalar values represent probabilities for each of the characters in our output vocabulary, C, O, N, E, and T. If we take the argmax of each of the vectors, which is the index corresponding to the highest probability, we are effectively selecting the characters which the model predicts with the highest certainty to occur at each step. Now we can introduce the first rule of CTC, which is that all repeated characters which are produced by our model are to be collapsed to a single character. However, almost immediately we should notice that this causes an issue, because it prevents the ability to predict words where 2 or more of the same characters occur adjacently. To prevent this behavior, a new token, called the blank token, is used. This new token is inserted between all target characters, and thereby allows us to predict repeated characters in the target transcription after collapsing. Let's visualize how this works with a simple 2-letter transcription at. Let us first insert the newly introduced blank tokens between every character. In this example, our model outputs 6 characters in total. Consider the following potential outputs: A followed by T followed by 4 blanks, then A followed by 2 T's with 3 blanks, and so on. Consider for a moment that all of these example outputs would produce the correct transcription after collapsing all repeated characters and then removing all blank tokens. An important realization is that all of these transcriptions either begin with the letter A or the blank token and end with the blank token or the letter T. Rather than attempting to write out all the possible predictions that would result in the target transcription, let us attempt to visualize this problem. Here, additionally, to be able to better differentiate them, we also include an index for the blank tokens. Consider now the model prediction of 4 blank tokens followed by A and then T. This path corresponds to a model prediction which would produce a correct target transcription. Note that we could never predict blank 1, A, and then blank 2 at the final time step and produce a correct transcript. Consider next the path of the model prediction of A, then T, followed by 4 blanks, which also corresponds to a valid prediction. Noting again, predicting blank 2, T, or blank 3 at the first time step would not result in a correct transcript. Therefore, we observe that all valid paths begin with blank 1 or the letter A and may pass through the same letter or any of the other subsequent letters in the target transcription, including the blank tokens, but must end with the letter T or blank 3. Valid paths may not skip any of the letters but may skip blanks. Only, however, if subsequent letters in the target transcription are not repeated. Considering the same target transcription at, where our model produces 6 outputs, how might we calculate the probability assigned by the model to each of the valid output paths? If we consider the 2 paths illustrated here, the probability of each path is the product of all the probabilities of the respective characters at the respective time steps. However, at face value, to calculate the total probability assigned by the model to all of the valid paths, which would result in the target transcription, becomes computationally intractable. But first, let's take a step back and consider why we would want to calculate the total probability of all the valid paths. As we illustrated earlier, our model predicts a series of output vectors containing probabilities of characters at each time step. What we would like to do is derive a function of the total probability of the target transcription with respect to these model outputs, from which we can improve the model prediction by updating the parameters of the underlying neural network after performing backpropagation and gradient descent. Currently, we are faced with the issue that calculating the total probability of all the valid paths is intractable. However, we can leverage the fact that many of the paths have, in fact, subpaths in common. With this in mind, let's consider the value alpha, which we define here as the probability of the subpaths which lead to blank 2 at time step 3. We will consider a more general formulation later on. Therefore, for the moment, let's ignore everything past time step 3 and blank 2. The valid subpaths include blank 1, A, blank 2, and then A blank 2, and then A, blank 2, blank 2. Therefore, the probability of alpha is defined as the sum of these 3 terms. Next, let's consider alpha A at time step 2. The valid subpaths pass through blank 1 and A, as well as A and then A. For alpha blank 2 at time step 3, let's pull out the common factor y blank 2 at time step 3. Let's also pull out the common factor of ya at 2. Here, we should be able to recognize that alpha A at 2 is in fact the first 2 terms within the brackets. Similarly, we can substitute the final term for alpha blank 2 at time step 2. What we have arrived at here is a recursive definition of the probability of a path passing through a specific character at a specific time step. This allows us to much more efficiently compute the total probability. And we're going to call this alpha variable the forward variable. This definition has 2 instances. Firstly, for all the blank tokens or the repeat characters, the valid preceding characters are only either the same character at the previous time step or the previous blank. For all other tokens, an additional term is included to account for the previous possible character at the previous time step. This is of course the case where the path skips the blank token. This allows us to rather conveniently find the total probability of our target sequence predicted by the model by simply calculating the summation of the last 2 valid alpha variables. However, we require a formulation which describes the total probability with respect to the model predictions at each output, and not only the final outputs. To this end, let's condition our probability such that we only consider the paths which travel through character A at time step 2. We will indicate this by saying that our new variable s is A at time step 2. Based on the rules we defined earlier, we know that at time step 1, the valid path passes through blank 1 or A, and then of course through A at time step 2. This is alpha A at time step 2. However, we do not yet have a formulation to calculate the probability of the valid paths proceeding from A onwards. Similar to our definition of alpha, we're going to define here beta as the probability of all the subpaths which begin from t at time step 4 onwards. Again, for the moment, let's ignore everything before time step 4 and character t. The valid subpaths are t for all 3 time steps, t followed by 2 blanks, or 2 t's followed by a single blank. If we consider beta of t at time step 5, the valid subpaths include 2 t's or a t followed by a blank. The only valid subpath for beta of blank 3 at time step 5 is preceded by another blank at time step 6. Next, if we pull out the common factors in the beta terms, we can again see a recursive behavior emerging. This then is the definition of the backwards variables, which again have 2 instances. The first is defined for all blank tokens or characters which are repeated within a word. This definition is composed of the probability of the current character at the current time step multiplied by the sum of the beta term of the same character at the subsequent time step and the beta term of the subsequent character at the subsequent time step. The second instance is defined for all other characters. As a reminder, this is necessary because if one had to consider the path which passes through A at time step 4, the valid subsequent characters include A, blank 2, and T. Now, we can leverage the forward and backward variables we have just defined to calculate the conditional probability that we mentioned earlier. Let's begin by multiplying alpha A at time step 2 with beta of A at time step 2. Recalling that these are defined as the probability of all the valid subpaths which either lead to or begin from a specific character. Note that on the right hand side of the equation we use the recursive definition we defined earlier. Firstly, we rearrange the right hand side of the equation. Then, if we multiply out the alpha and beta terms whilst incorporating the probability of A at 2, we are left with 6 terms. If we consider the first term, highlighted in blue, we can identify this as the partial probability of all the valid paths which begin at blank 1, pass through A at time step 2, and then pass again through A at time step 3. Similarly, if we consider the term highlighted in orange, here we have identified the partial probability of the valid paths which pass through A at time step 1, A at time step 2, and then T at time step 3. These 6 terms then define the conditional probability of all valid paths which pass through A at time step 2. Now we can expand upon our definition of variable S, where we defined vector bold S as a single valid path, and we defined capital S as the set of all valid paths. We can then use this definition to incorporate the 6 terms within a summation which is defined as the sum of the probabilities of paths bold S from the set of all paths capital S, where scalar S at time step 2 is A. It may be practical to sit and consider this last function for a little while. Here, we rewrite it with a y term on the left-hand side of the equation. Again, here is capital S, which is defined as the set of all valid paths of the target transcription, with a few examples. Let us proceed with our derivation by generalizing the time step to any time step small t, and let us additionally sum over all the valid characters which appear in our target transcription at this generalized time step. This then gives us the total probability assigned by our model to the target transcription. Very conveniently, the innermost sum is simply the product of the alpha and beta terms divided by the probability of the specific character at the generalized time step. This then becomes our objective function. But the question remains, how do we improve our network's predictions utilizing this function? Generally, in training neural networks, this is accomplished by maximizing the log likelihood. More specifically, we consider descending the partial derivative of the negative log likelihood of our objective function, taken with respect to model output y at time step t at specific character k. There are two important steps within this calculation to take note of. Firstly, the partial derivative of any of the terms within the summation will be 0 when y of I is not y of k. Therefore, we are left with a single term from the summation. Secondly, one should note that the summation in the numerator remains because k can either be a repeated character or a blank character, which occur multiple times within the target transcription. For example, if we are calculating the partial derivative with respect to the blank character, therefore k is blank, the numerator is the sum of the product of the alpha and beta terms for blank 1, blank 2, and blank 3. This becomes considerably easier to understand if we consider the derivative with respect to the vector y, which contains the model probabilities for each character. That is, the blank character, a, and t. Let's first substitute our derivation of the partial derivative for each position in the vector and remove the common factor p of at. In the summation, we only consider the characters which are the same as the target character. In our example, this is either the blank character, a, or t as shown. Then it becomes clear that the numerator of the derivative for the blank character is the sum of the product of the alpha and beta terms for blank 1, blank 2, and blank 3. While for the a and t characters, there are only one term in each of the respective numerators, because those characters are not repeated in the target transcription. Thinking back to much earlier in this video, we showed how the character probabilities of our network are calculated. These were defined in terms of a sequence of vectors denoted as y, each at a specific time step. Now we can tie in the derivative of our objective function, and using the chain rule, we can backpropagate the areas through the softmax function to update the fully connected layer, and in some instances, even the underlying neural network. There are of course many more elements of CTC to describe, such as the various decoding strategies and how language models are incorporated into said decoding. However, this brings us to the end of our discussion for this video. I hope you found this description enlightening and that the innermost workings of Connectionist Temporal Classification, or CTC, have been demystified for you.